Welcome to the office. We want to continue taking a look at permutations. And what we would like to consider now is a formal definition of what a permutation is, right? The definition that we are concerned about as trying to look at groups here. Once we recognize what a permutation is, we can talk about the collection of permutations, and then we want to define a binary operation on them. Once we have a set and a binary operation, we can then discuss uh, if that binary structure, right, is that binary structure a group, which is what we'll get to shortly. So first, a new definition or our definition for a permutation. A permutation of a set A is simply a function that takes A and maps it to A that is both one-to-one and onto. And this should make sense, right? Based on what we talked about in our previous video, all we're doing is taking this collection of objects, A, and mapping it back to A, where the input of 1 is 2, the input of 1 gives us an output of 2, the input of 2 gives us an output of 4, input of 3 gives us an output of 1, input of 4 gives us an output of 3. This, right, our function is defined in that way. By recognizing this rearrangement is what is given by, right, identifying 1 with 2, 2 with 4, and so on. Okay, that observation is explicitly expressed here. And what we would like to do is we would like to give a little bit better representation for it. So we'll look at that in just a moment. But this is the idea. We have a function that is one-to-one and onto, and that is a permutation. All right. So what is the binary operation on a set of permutations? Well, permutations are functions. How do we combine functions? How do I take two functions and come up with a new function that has the same domain and range, or domain and codomain rather? And there's two different ways that we can do that. When we are working with numbers specifically, well, I say two, but really that's not quite right. Well, yeah, okay. So how can we combine functions? The usual algebra of functions, addition, subtraction, multiplication, and division. However, that doesn't necessarily make sense here because if I add two of these things, right, our objects might not even be numbers. So that doesn't necessarily make sense. But even if I took this as an example, I couldn't take f plus g and have outputs of 3 plus 4 giving us 7 because 7 doesn't belong in the set 1 through 4. Okay, so addition doesn't make sense. Subtraction similarly won't. Multiplication, same problem. Division, of course, these aren't even fractions. So those normals don't. However, we do have function composition. Since our functions go from A to A, that means if we have another function, it will just take it from A to A again. And since they're all one-to-one and onto, we get exactly what we're looking for, another permutation. So the binary operation on the set of permutations, what is it? So for permutations, let's go with sigma and tau. So for permutations, sigma and tau, their composition, let's go with sigma composed with tau, is another permutation. Maybe you want to point out so the composition goes from A to A, okay? So function composition gives us another permutation. Now, in order to verify that, we would have to verify a couple of things. Now, I'm going to make a bold assumption here, okay? The bold assumption is that we've seen a proofs course, and typically presented in a proofs course is that the composition of bijective functions is also bijective. Okay, so we need to have that specific quality, and I would encourage you to verify it. So, sure, let's say, can you verify this? If you think that you can, excellent. Jot down a few notes on how you think it goes. If you're not sure that you can verify it, why don't you check it out, right? You know, if you have two functions that are one-to-one and onto, Can you verify that their composition is also one-to-one and onto? Now, you could look at the specific instance of the same domain and codomain, or you could use the appropriate collection, A to B and then B to C, and compose appropriately. In this case, we can compose in either direction, right? Sigma tau or tau composed with sigma because they're both from A to A. So that's absolutely fine. No big deal at all. However, we should also recognize that function composition in general is not commutative, so we're not going to get that nice characteristic, right? We don't necessarily have commutativity of permutations, okay, because we're talking about function composition. The notation, so let's see here, the notation used for, let's call it sigma composed with tau, just as we have written up here, is multiplication. That is, we write it as sigma tau, right? They're right next to one another. So this is not what we do. We actually do this. We do not use a symbol, but we do need to understand that as sigma composed with tau. In order to then implement this, if I wanted to take sigma tau of A, for example, okay, so we're going to plug in some number, plug in 2. Well, sigma is going to take 2 to 4, and tau is going to take, well, actually, make sure we do it in the right order, right? We have to do tau first in this case. We recognize that this is sigma composed with tau. We don't need this notation, but we definitely should move to sigma composed with tau of A. Okay, so we want to recognize that this is function composition. Therefore, when we go to evaluate such an expression, we would have to evaluate tau of A first, and then sigma of that result. So we work from right to left in this case, not left to right. Be very, very cautious about that, all right? So notation there. Make sure you are familiar and comfortable with using multiplication as our symbol for the binary operation, and recognizing that as composition. Okay, composition written as multiplication. So now we want to talk about our representation of permutations. Well, let's use the example that we looked at just a moment ago. So 1, 2, 3, 4 being mapped to something. If I wanted to write all of my permutations in this way, so 2, 4, 1, 3, 2, 4, 1, 3, this would be fine. It's a bit cumbersome. Technically, what we could do is we could also write it as, right, working with 2, 4, 1, 3. This is a little bit weird, especially as we go to work through combining them a little bit later. If you put parentheses around it, that's going to mean something that you don't really want it to, right? Because this is an ordered four tuple. So it's just a little bit weird. So we don't really like that particular notation because it has meanings that we're already familiar with that are not regarding our current context. So let's use something different. Let's take actually something a little bit more similar to what we did in our first video, where I wrote down the original arrangement, 1, 2, 3, 4, and then below it wrote 1 is mapped to 2, 2 is mapped to 4, 3 is mapped to 1, 4 is mapped to 3. We can do that presentation. So I can take my 1, 2, 3, 4, and I can recognize that I am mapping them as 2, 4, 1, 3. Now you want to be careful about spacing, because sometimes you'll end up with 2-digit numbers right when we get to large enough sets here that we're talking about. And if you end up with 2-digit numbers, then you want to make sure that the spacing is appropriate so you can recognize, 1 and 2 versus the number 12. Okay, so just be cautious there. But then to help us designate this as an object, we're going to put it inside of parentheses. And so we could define tau in this way. This gives us, for example, that tau of 1 is equal to 2, tau of 2 is equal to 4, tau of 3 is equal to 1, and tau of 4 is equal to 3. So we have this representation, we have this representation, and then we can evaluate the function tau. Okay? Tau is a permutation. We're going to use this notation for this section. We'll actually develop a new notation a little bit later that's similar to what we wanted to do here, but is definitely an improvement over this as well. All right, so we have, again, we have what is our function, or what is our binary operation. Our binary operation is composition, and our representation is going to be using these things right here. We'll take a look at an example in our next video where we go ahead and compose two functions. So join me back here in the office in just a little bit for that example.